All right, what'd you get for that? Should look something like that. What patterns did you notice? If dy dx just equals y, then whenever y is 0, the slope's going to be 0. I'm just sort of resketching it here. Whenever the y is 1, the slope's going to be 1. So these are all have y coordinate 1, they have slope 1. Whenever the y coordinate is 2, the slope's going to be 2. Right? So you can sketch it actually pretty quickly. Right? And then 3. When the y is negative 1, the slope's going to be negative 1, so, like that. So you can sketch that quite quickly. Now, that was a quick sketch, and it actually looks not bad. I'm not finished. I did this one with a ruler. It really doesn't look much better. All right, what else did I ask you to do on this one? I asked you to sketch the particular solution through 0, 1, and 0, negative 1. All right, so where's 0, 1? That's right here. Okay, what does our particular solution look like? So I can't cross this, right? I don't want to have a non-zero angle right there. So I want to go more parallel to each of these slope lines. But then when I'm coming down here, I can't cross these at an angle. So it's not that you can't cross a line. You have to always be parallel to the line. Right, I sort of crossed this one. It's like you can't not hit them. You can hit them. You just have to hit them parallel. All right, so that's through the point 0, 1. What about the point 0, negative 1? Well, here, let me use a different color for that one. Why not? 0, negative 1 is going to go, following these slopes, it's going to go like that. So again, it's a little bit of an art form to follow the currents that you're seeing, like they were ocean currents. Okay. What about this? What function is suggested by the slope field? What functions does this look like? Well, it looks like y equals e to the x, doesn't it? And so what this one down here is y equals negative e to the x. Y equals negative e to the x. Yeah. So that's basically what we're looking at here. And we can do, so you really have y equals any constant a times e to the x. If we look at all the different possible solutions here, y equals some constant times e to the x. Y equals k e to the x. That's what we've got there. All right. So that's interesting because what you're looking at is, I put a k because we could have any, this one's pretty bad. We could have any vertical expansion or compression. And if k is negative, then we're going to have reflection over the x-axis. So we have all these down here. Right, so what we're looking at is vertical expansions and compressions of the same function, which is e to the x. Well, why is that the solution to dy dx equals e to the x? Well, if y equals k e to the x, then dy dx equals k e to the x, which is the same as y. So if dy dx equals y, essentially it's saying if a function is its own derivative, I do the derivative of a function and I get the same function I had. There's only one function that does that. It's e to the x, but it could be multiplied by some constant. That's going to be important to us later. All right, now what we're going to do is, that's enough of me talking about slope fields. So it's time for you to do some. So here's the homework assignment. I'm doing something a little bit weird. So first of all, we've got the mixed integral review. So that's, that's just 7 problems. They're hard, but it's only 7 problems. All right, and then I've got, for chapter 6, page 328. So one thing about page 328 that I was going to point out is, just look at some nifty slope fields. These are things that slope fields look like. Partly it's, this is a matter of just getting a visual sense of what slope fields can look like. And you could look at all these examples. They're pretty interesting. They're all interesting. You could do a whole course on this. In fact, you will, if you do engineering, you will do differential equations. You'll do a whole course on this stuff. All right. What I want to change the directions a little bit there. Here it says construct a slope field. Copy the graph at right. All right. Well, that graph's a little small. Here's what you're going to do instead with 29 through 34. I'm changing the directions. This is all posted in the Google Classroom and on the homework assignment sheet on the website. So chapter 6, page 228 is what we're just looking at. We're doing 29 through 34 odd. What I want you to do is construct a 3x3 slope field and sketch the particular solution through 1, 2. I want you to do that for every one of those problems, 29 through 34. So basically you're going to produce something that looks like this. All right. But make sure it only goes 3x3. Don't make the whole thing. Just only go up to 3 and down to -3 and over to -3 and over to 3. I mean, you could do more than that if you want, but I don't recommend it because you've only got so much time. Believe it or not, I actually am aware of that. And then the second part is 35 through 40. So 35 through 40. Now it's just matching. It just says match, right? Match the differential equation. So all you really have to do is put A, B, C, or D. You know I'm not going to be happy with that. So therefore, you need to complete each matching with a brief justification. What does a brief justification mean? Well, think about using patterns. Like let's say I'm looking at B here. So what stands out for me on this graph B is that I notice that the slopes are all undefined when x equals 0, and the slopes are all 0 when y equals 0. That tells me I'm looking for something with y in the numerator and x in the denominator and not much else going on. Y in the numerator and x in the denominator and not much else going on, right? So I can justify this one, 39 is B. Hey, I just gave you an answer. 39 is B because the slopes are horizontal when the slopes are horizontal when y equals 0 and vertical when x equals 0. So you're going to look for patterns like that and basically justify each one of those with a pattern, but I do want you to give a brief justification for each of those matching in 35 through 40. That is it.